For a moment, astronomers thought James Webb had found something almost impossible. A tiny red object appeared in one of Webb's deepest images. It was so faint at shorter infrared wavelengths, and then suddenly so bright at longer wavelengths, that the simplest interpretation placed it at a redshift of about 32. If that were true, its light would have begun traveling toward us when the universe was only around 100 million years old. Astronomers gave the object a nickname, Capotauro, and it seemed to be sitting right at the edge of cosmic history. But there was another possibility. What if Capotauro was not unimaginably far away? What if it was practically in our own backyard? A few years later, Webb looked at the same patch of sky again, and this time Capotauro had moved. That tiny motion changed the entire story. Because distant galaxies do not visibly slide across the sky over just a few years, a nearby object can. Capotauro was not one of the earliest galaxies in the universe. It was almost certainly a tiny, extremely cold brown dwarf inside the Milky Way. To understand how astronomers could confuse those two things, imagine looking through a dark forest at night. Far beyond the trees is a red lamp sitting on a distant mountain, but much closer to you is a tiny glowing ember floating through the air. If both produce almost the same color through your camera, a single photograph cannot tell you which one you are seeing. You need another clue. You wait. Then you take another photograph. The distant lamp stays in exactly the same place. The nearby ember moves. That is essentially what happened with Capotauro. The story began with the way astronomers search for extremely distant galaxies. As the universe expands, light traveling through space is stretched toward longer wavelengths. The farther away a galaxy is, the more its light is shifted toward the red and infrared. But something even more useful happens to light from the earliest galaxies. Hydrogen between those galaxies and us absorbs much of their shorter wavelength radiation. This creates a dramatic break in the spectrum. On one side of the break, the object almost disappears. On the other, it suddenly becomes visible. Astronomers call this the Lyman break, and Webb is exceptionally good at finding it. A telescope does not necessarily need a detailed spectrum for every faint object. Researchers can first photograph the same area through several filters. Imagine placing different colored windows in front of a camera. An ordinary galaxy may appear through several of them, but a very distant galaxy might suddenly vanish through all the shorter wavelength filters and reappear only in the reddest ones. That is called a dropout. Capotauro was an extreme dropout. It was essentially invisible below about 3.5 micrometers, then dramatically brighter around 4 to 5 micrometers. The drop was more than 3 magnitudes. When astronomers tested different galaxy models, one interpretation fit remarkably well. The apparent break could be the Lyman break shifted all the way to around 4 micrometers. That implied a redshift close to 32. If Capotauro really lived at that distance, the implications would have been enormous. Webb has already pushed confirmed galaxies back to roughly a few 100 million years after the Big Bang, but redshift 32 would go much farther. We would be looking toward an era close to the formation of the first stars and the first black holes. A galaxy visible that early would raise immediate questions. How did enough gas collapse so quickly? How had stars already begun forming? And how could an object become bright enough for Webb to detect across almost the entire history of the universe? But the original researchers noticed a problem. Capotauro looked like a point. It did not clearly appear extended like a galaxy. And there was another kind of object that could produce a surprisingly similar infrared pattern, a brown dwarf. Brown dwarfs occupy the strange territory between stars and planets. They can form like stars, collapsing directly from clouds of gas. But they are not massive enough to sustain normal hydrogen fusion in their cores for billions of years. Some begin hot and bright, then they slowly cool. Eventually, the coldest brown dwarfs can reach temperatures closer to planets than stars. The coldest known class is called the Y spectral type. At those temperatures, their atmospheres contain molecules such as water vapor, methane, and ammonia, and those molecules absorb infrared light very strongly at certain wavelengths. Now the trap becomes clear. A distant galaxy can disappear in shorter wavelengths because intergalactic hydrogen absorbs its light. A cold brown dwarf can disappear at similar wavelengths, because molecules in its own atmosphere absorb the light. Two completely different physical processes can create surprisingly similar colors. One object could be almost at the beginning of the observable universe. The other could be floating inside our own galaxy. From one set of images, they can masquerade as each other. So astronomers needed a test that had nothing to do with color. They needed motion. The original Webb images had been taken years earlier. New medium-band INEAR-CAM observations gave researchers another view of the same field roughly 3.5 years later. The team then built a reference frame using 68 compact sources around Capotauro. Think of those objects as nails hammered into the background sky. If Capotauro were a distant galaxy, it should remain fixed relative to them. Instead, it shifted. Not much. The total displacement was about 132 milliarseconds. That is an absurdly tiny angle. If you divided a single degree into millions of pieces, this movement would occupy only a small handful of them. But Webb can measure extremely small changes, and the signal was strong enough to exceed 6 sigma. The source was moving at roughly 38 milliarseconds per year across the sky. That effectively ruled out a distant galaxy, an active galactic nucleus, and even an extragalactic supernova interpretation. Capotauro was nearby enough for its motion through space to become visible. The researchers then compared its infrared colors with known brown dwarf spectra. The best match was a Y-type brown dwarf around spectral type Y1, with an estimated temperature near 350 Kelvin, that is only about 77 degrees Celsius. For something that formed like a star, that is extraordinarily cold. The estimated distance was around 730 parsecs, or roughly 2,400 light-years. That still makes Capotauro distant by brown dwarf standards. Most known Y dwarfs are much closer because these objects are incredibly faint. Capotauro may therefore be one of the most distant Y dwarfs discovered so far. And suddenly, the failed galaxy discovery became interesting for an entirely different reason. Picture the Milky Way as a vast city at night. Stars are the bright buildings. Planets are almost invisible objects moving around them, but between those stars may be enormous numbers of dim brown dwarfs, too faint for older surveys to find at large distances. Webb was not designed primarily to hunt these objects. It found Capotauro while staring deep beyond the Milky Way, searching for galaxies billions of light-years away. In trying to see the edge of the universe, Webb accidentally found one of the faintest residents of our own galaxy. That creates an important warning. As astronomers push toward higher and higher redshifts, the number of convincing galaxy candidates becomes very small. A single strange object can therefore have a large scientific impact. But the farther back researchers try to look, the easier it becomes for unusual nearby objects to imitate the signal they are searching for. At redshifts around 10 or 12, astronomers already have large samples and increasingly strong spectroscopic confirmation, but push toward redshift 20, 25, or 30, and the game becomes much harder. Cold Y dwarfs can produce a sharp rise in brightness around 4 to 5 micrometers, because water, methane, and ammonia suppress shorter infrared wavelengths. If that rise is mistaken for a Lyman break, a brown dwarf in the Milky Way can suddenly appear, mathematically, to be a galaxy from nearly the beginning of time. Capotauro therefore gives astronomers a new rule. Color alone is not enough. Future searches for extreme early galaxies will need better brown dwarf templates. They will need medium-band observations that reveal more detail in the shape of the infrared spectrum, and whenever possible, they should return to the same field years later. Because motion is one thing a distant galaxy cannot easily fake, there is a strange symmetry to the whole story. Capotauro first became exciting because it seemed so distant that its light might have come from an era before normal galaxies should have been common. Then it became exciting again because it was much closer. Instead of revealing the first chapter of galaxy formation, it revealed how incomplete our census of the Milky Way may still be. And one more observation could make the story even better. The current estimate of Capotauro's distance comes from comparing its brightness with similar brown dwarfs. A future observing epoch could measure something called parallax. As Earth and Webb move around the Sun, a nearby object appears to shift slightly against the more distant background. Measure that tiny geometric wobble, and astronomers can determine the distance directly. That would tell us exactly where this strange object sits inside the Milky Way. Capotauro began as a candidate for one of the most distant galaxies ever imagined. Now it may become a laboratory for studying some of the coldest star-like objects we can detect. And that is not a story about scientists making a mistake. It is a story about how science corrects itself. First, the colors suggested something extraordinary. Then another explanation appeared. Instead of choosing the more exciting story, astronomers waited for a test that could separate them. 3.5 years later, the universe supplied the answer. The tiny red dot moved. And with a shift smaller than almost anything the human eye could ever perceive, an object was pulled from the dawn of the universe and placed back inside our own galaxy.